one of the neatest applications of absolute value equations and inequalities is dealing with the idea and concept of what we denote as tolerance. You might have like siblings or something like that that might bug you from time to time, and you have a certain tolerance level or willingness to tolerate that until you just get like angry at them or something like that, right? Or like if you think about like temperature, like you might be able to tolerate a 65-degree temperature in your home or a 75-degree, but like, you know, if it was like 102 degrees, like then that just gets very, very warm, right? And so you have a certain sort of tolerance level. So just kind of thinking along those lines. So let's say like, I don't know, if you're willing to tolerate between 65 degrees and 75 degrees, like if you feel like that's a comfortable temperature where you live, then we can actually model that using this sort of a representation. And I'll kind of break apart what all of this means once I write this all out here. So by middle, what that really means is the middle of your interval. So in this case, it would actually be the number 70. So if we were to do the specifics to this example, then what I've denoted right here is the distance of the quantity x minus 70, and then I put a box right there, and that box is to be filled in with like a less than or a greater than or a greater than equal to, less than or equal to, or an equal sign depending on the particular situation. And then your tolerance is how far you're willing to tolerate from the middle. So this right here is going to be your tolerance. So your tolerance would be a distance of 5 because you could go plus or minus 5 on either side of the middle. And so what we want is we want that distance of x minus 70 from 0 to actually be less than or equal to 5 because you're within a certain distance right there. And so this would actually model what's going on right there. So rather than just writing like the inequality 65 is less than or equal to x is less than or equal to 75, so that right there would write that as a compound inequality, whereas this right here, this would write this as an absolute value inequality and model what's going on. But either way, that and that are equivalent, okay? All right, that gives you kind of a rough introduction. Let's take a look at some examples we can get this to really settle in. So we know that a regulation baseball for Major League Baseball, MLB, should be 5.125 ounces, but it has a tolerance of 0.125 ounces. A tolerance means that it could go above that 5.125 that much or below it that much. So we want to write an absolute value inequality that shows the acceptable weights of the baseball. So in terms of just understanding the acceptable weights of the baseball, we know that kind of the average or typical weight it should be is 5.125. But since the tolerance is 0.125, then if you add 1.25 or 0.125, you're going to end up with 5.25 there. But then if you go 0.125 that way, you're going to end up at 5. So it turns out that the acceptable weights of a baseball are going to be anywhere between 5 and 5.25. So if we write this as an absolute value inequality to represent the weights of the baseball, so if I pick the variable b, let's say, to represent the weight of a baseball, then if you subtract the middle of that interval, so 5.125, then because we're within a certain range, we need the distance to be less than, and I guess it could be equal to, because we can include the endpoints, the tolerance. And the tolerance is how far away, plus or minus, you're willing to go from the middle. So that absolute value inequality represents the range of the possible weights of the baseball there. This is saying that a poll shows that 52% of voters are likely to vote for the incumbent. The poll shows a margin of error plus or minus 3 percentage points. So it could go plus or so up to like 55 or as low as 49. Write an absolute value inequality to represent the possible percentage of voters that will vote for the incumbent. So it's just saying, okay, 52%, but it could actually be 55 or it could actually be 49 because plus or minus 3. And so, yeah, if we just say V is the percentage of voters, let's say, just subtract the middle of 52, and then it has to be anywhere in between, so I guess so less than or equal to, and then your tolerance is 3, because it could be plus or minus 3 on either side, and then you're done right there. That models it with an absolute value inequality like it was specifying. Okay, this gives us more than just baseballs, I guess, some other sorts of balls that are used in sports. The acceptable ranges of weights of balls for different sports are shown in the table. Write an absolute value inequality for the acceptable weights of each ball. So if I just take an example like, I don't know, let's say like a lacrosse ball. So a lacrosse ball can be acceptable if it is as low as 142 but as high as 149. So these are the ranges. So if I wanted to write this as an absolute value inequality, so let's use L for lacrosse ball. I want L minus the middle of the acceptable ranges, which we don't know. So we're going to have to find what that is. So to find what that is, if you've got two endpoints, you can find the middle by averaging that. So if you did 142 plus 149 and you divide that by 2, that's going to give you 291, which then you'll want to divide by 2. So when you divide that by 2, you end up getting 145.5, and that would be the exact middle. And then because you're within a certain interval, you'd want that to be less than or equal to. And then you want your tolerance, and this right here would be your tolerance, how far 145.5 is from 149, or how far it is from 142, and that turns out to be a distance of 3.5. So you have a tolerance of 3.5, and that's going to give you an absolute value inequality for the acceptable weights of each ball. Now notice that if the question was actually asking for what are the rejectable weights, then the rejectable weights, right, would basically be if this is where 142 is and this is where 149 is, then anything over here or anything over there would be rejectable because then it's too light or too heavy for what's acceptable in lacrosse. So if you wanted to write that as an absolute value inequality, basically you can just kind of keep this the same almost. The only thing that you need to make different is now you'd actually want it to be well, actually, we don't want it to be equal to, because then it would be legal. You need it to be strictly greater than the 3.5, have a distance of 3.5, or more from 0. And that would be rejectable weights if you were asked for something like that. And then one last example right here. So hypothermia and hyperthermia are similar words, but they have opposite meanings. They're both emergency medical conditions. So hypothermia occurs when your body temperature falls below 95, so that's when it's really cold. And then hyperthermia occurs when your body temperature is above 104 degrees, so too hot. Write an absolute value inequality to describe the safe body temperatures. So we'll consider safe to be, not too cold and not too warm. So safe, I guess, would be when you're 95, because it says if you're below 95. So we'll assume you're safe if you're 95, so we'll include that all the way up to 104. So that would be the interval. We want to represent that with an absolute value inequality. So we need the middle of this interval. So you'll have to average the 95 and the 104 together and come up with what that would be. Turns out that it's going to be 99.5 is going to be the midpoint of those values right there. So the safe body temperatures then would be, let's use T for temperatures minus the middle, and we'll absolute value that quantity. Since we want to be within a certain range, we're going to have a less than or equal to, and then you need a tolerance, which is the distance from the midpoint to one of the ends, and that distance ends up being 4.5. So that's going to model the safe body temperatures. And then part B asks to write an absolute value inequality to describe the dangerous body temperatures. So dangerous, I'll just use the number line from up here. Right there and right there are going to specify danger. So it just turns out that we can take the same absolute value inequality that we had, but just kind of turn it around and make it a greater than 4.5 to specify that we're going to deal with those more extreme, colder or hotter temperatures.